here we go. We're going to start, just going to jump into Canvas real quick and take a look back at the week that is occurring. We are in week 12. Right, we're all the way down to Thursday. Today we will be going into, we'll basically finish up section 5.1. We'll be talking about randomness in simulation and how probability is used within those. We'll see some examples, some definitions. This is mostly just kind of information in this latter part of the section. There's no real like new math. Though there is some, within the simulations, there's a little bit of mathy kind of stuff, but there's no like formulas or anything like that today. It's mostly just information. The chapter 2 self-assessment is available. I realized Tuesday afternoon that I hadn't published it, even though I finished making it. Oops, sorry. So that is now available for you guys to do. Again, you have about 2 weeks or so to do that before it will be marked as incomplete. So there's that. We have our discussion board from Monday, which I have not looked at yet. Hopefully that's going well. All the resources for Monday's class are available. And yeah, we'll be updating these live class resources as everything becomes finished and published. We've already got everything up through period 3 in there. So yeah, we've got most of Canvas is all good to go for the week. Yeah. Does anyone have any questions, comments, or concerns about Canvas for this week or previous weeks? I'm gonna go with no. All right. Go. We'll do a quick preview of the chapter 2 self-assessment. You're going to need table A for this, or be able to get similar type of things from your calculator, your graphing calculator. Yep. I do have it suggested here for the free response question, question 1 on the quiz. I think it will work best to do your work on paper if you can, and then upload a picture of your work in the text entry box. If you need help, please let me know. Sometimes this can be easy, sometimes it can be hard to get a picture in there. It just depends on what you're working with. So there's that. Here is the question. We're looking at distribution of scores on a recent test. They have a mean of 22 points and a standard deviation of 4. You find the proportion of students who scored at least 25 points. What's the 31st percentile? We're going to do a transformation to the scores, and then consider another set of scores. Right, so there's a few parts to this one. Really having you work with percentiles, that proportion under the curve, the density curve, the standard normal curve, table A, and all those things, okay? Again, and if you need help with this, if you're stuck on any part of it, please email me. Those of you who have emailed me know that I respond in a pretty timely manner, and I'm more than happy to help. Obviously, I'm not going to give you the answer, but I will explain what you may need to do. So please keep that in mind for this. The other two parts look exactly as they have in the other self-assessments. You have the reflection and the selection of your level of understanding. All right. And that's about it. Any questions about the self-assessment for chapter 2?
Nope, but I'm tired.
Huh?
Nope.
Nope.
I'm tired.
Right, all right. So there's that. Alrighty, so then let's get into today's lesson. So let's get into it. It is Thursday, November 12th, 2020, and today we will be talking about randomness and simulations. Randomness. All right, we've all understood what randomness is. Randomness kind of applies to things that we believe happen in random ways that we can't really tack it down. It's just random. It may or may not happen. All right. Probability allows us to predict what would otherwise be random and unpredictable. So things that may appear to be random might over time develop a pattern. And if it does, a probability can help us explain that pattern, or just see what the pattern is. Right. One drawback is that probabilities are rarely correct in the short term. And when things don't seem to fit, we tend to try and explain them without probability in mind. We try to figure out, okay, why did it happen? Maybe there is no explanation. Maybe it's something happened where it just went on a streak, or we have a run of this certain thing happening and we can't explain it. Possibly. One of the key things you want to come away with today is the difference between something occurring in a short-term time period and a long-term time period. All right. If something just doesn't happen to fit into what we think should happen based on the probabilities or based on experience in the short term, that doesn't mean it still isn't fitting into our probability model. It's just a short-term period and it just didn't work out that time. That happens. Right? You can have, think about it in sports, you can have someone who averages, 75% from the free throw line, have a game that they don't make any free throws. Right? It doesn't mean that they're never going to make them again, or that now they're at 0%. It just means they had a bad game. And that just doesn't necessarily, that short sample doesn't fit into the long-term results. Okay. And we'll see, for example, suppose you flipped a coin 6 times. Right? Which of the two outcomes below seem more probable? Right? We have heads is H, tails is T. Here's our two possibilities. Do you think the one on the left or the one on the right is more likely to occur? Please type your answer in the chat. All right, we got 1 for the left, 2 for the left. Ooh, another one for the left. Left. Right. All right, Taylor chooses the left-hand side. Daniel wants to say it's the left, all right. No, everybody's being lefty today, huh? Nobody thinks, there's no love for the right-hand side. Fernando is going with the left-hand side. Can it be both? Oh, maybe. Antonio brings up an interesting point. Could it be both? Maybe. Esmeralda says it's the left. Yes, Valentine.
It could be different. It depends on the coin, all right? It doesn't have to be on one side. It depends on the coin.
Depends on the coin. So you're saying some coins are fair and some coins aren't?
Yes, for example, if you flip the coin, it doesn't matter. It could be heads or tails.
True.
It's just a coin thing. Depends.
Yeah. So you bring up a good point. You put voice to a good point. Same thing that kind of Antonio is alluding to in the chat too, right? Can it be both? The odds are slim, but it could be both, right? Depends on the coin. Coin's either going to be heads or tails, right? Those are the only options. So when we ask which one is more likely, right? Are these two outcomes showing different overall outcomes? is there more heads in the left-hand side than the right-hand side, or more tails in the left-hand side than the right-hand side?
It could be 50-50.
Well, I'm asking specifically with these two sets here. We have heads, tails, heads, tails, tails, heads, 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 tails, tails, tails. Are they actually different outcomes? Did we get a different number of heads and tails within the 6 flips of the coin?
No.
No, right? So the only difference is the order in which these things happened, right? It's the only difference, right? Probability doesn't care about order, right? Both of these outcomes are equally likely if we don't care about the order, right? There are circumstances where you will, I don't know if it happens in this class or not, but when I took probability in college, you had to consider order in some of the problems. In this case, we're just thinking about probability, which one of these two scenarios are more likely without order coming into play. They're the same outcome. All intents and purposes, there's six flips of a coin. We got 3 heads, 3 tails in both. So they're equally likely because they're the same outcome. All right. So that's a distinction you have to make when you're thinking about probability and likelihood, right? Where the order in which things happen doesn't necessarily matter. So we continue with this idea of randomness. Probability only says what is likely to happen in the long run, right? Over hundreds and thousands of iterations and simulations of an event. In the long run, about half the flips of a coin will be heads and half will be tails. Right? We know that. We've seen it happen. The order in which the outcomes occur is not a factor and does not change the long run probability. Right? We could have a run, we could flip a coin 100 times and the first 50 could all be heads. Right? The probability of the first 50 being heads is very small, but not 0, which means it could happen. Right? And then we could have the next 50 all be tails. And again, the probability of getting the first 50 heads and the second 50 tails, very small, but not 0. Again, there's different ways we can break down probabilities and this and that. We're just considering just overall cases right now where it's like 50-50 chance or flip of a coin. Hopefully I'm not confusing you. I feel like I added more things into this than were necessary, but it's interesting stuff. So again, probability has to do with long-term, long run, not short. And order, the order in which things happened, doesn't really matter. It's not going to have an effect on the long run probability. Therefore, we have the law of large numbers, which we introduced on Monday, right? Because of this idea of long run and order not necessarily matter, not necessarily, but I can't speak. Order not mattering, right? We have the law of large numbers, meaning over time, long time, many iterations, this probability is what we see in the pattern. So there's a myth though, right? This happens a lot with gambling, we'll say. The law of averages, because you can think of it as like someone playing blackjack or something like that. Because they've lost so many hands in a row, they're due a win, right? That's what, you know, gamblers have this attitude like, I'm due one now. I'm due one. Law of numbers, law of averages, right? I'm gonna win at some point. Well, let's do a more simple example. Imagine flipping a coin 6 times and getting 6 tails in a row. Again, not a very high chance, not a high probability of getting 6 tails in a row, but not 0. Could happen. If you believe in the law of averages, you might believe that the next toss should surely be a heads, as a head is due to appear, right? 6 tails in a row, the next one should surely be a head. We've had enough tails. Oh, well, lo and behold, the next flip is also a tail. Right? Entirely possible. How could this be? Well, to put it simply, the coin has no memory and doesn't care what you think. The coin doesn't know that it just landed on a tail the time before. It just got flipped and landed on a tail again. It doesn't care that you think it should be a head because there's been so many tails. It's just a coin. It has no feelings or emotions. It's going to land and you're going to see what it says. That's it. The same thing happens with gambling. And this is what casinos count on, right? Someone believes that because they've seen a certain outcome so many times, a new outcome should reveal itself. A new outcome should happen. Because based on averages, based on the probability, law of averages, I should win at this point, right? The machine, the cards, whatever, doesn't care. It has no idea what came previously. It's only going to do its job and produce another outcome. That's it. The myth is that future outcomes must make up for past imbalances, and this is just not the case. It's not how it works. In the long run, things will even out. This is the law of large numbers playing out. It has nothing to do with the law of averages. That's not a thing, right? As far as probability is concerned, we have the law of large numbers. However, like if you're thinking of someone gambling, for it to quote unquote even out, for them to get to that win because of the law of large numbers, could take a really long time and several thousands of iterations to really even out. But as we all know, the house is always favored, meaning that they always have the advantage in all the games. We're talking about casino games, and the probabilities of you winning and them losing, minuscule. So there's that. Any questions so far?
No.
No. All right. Cool. So now we're at a definition. We're going into simulations, which we've kind of talked about already. We've done one previously. The imitation of chance behavior based on a model that accurately reflects the situation is called a simulation. Right? The 1 in 6 game where we rolled dice to simulate buying sodas and winning a prize, right? We did on Monday. The simulation allowed us to quickly determine if the probability was reasonable without going out and buying sodas, right? The die that you virtually rolled simulated the purchase of a soda and whether or not you won. We rolled it 7 times because there were 7 friends. And so each 7 rolls was one simulation, right? One repetition of the simulation. And we did that a bunch of times. I think in your guys' class, we had like 68 repetitions of the simulation. Oh, my hair is just, ugh. I need to cut my hair, guys. All right, so we've seen a simulation. We did one. Now, there is a set of 4 steps to perform a good simulation, which we'll get to next. But first, does anyone need another moment to write down this definition? Or anything else? Yes, okay. I will wait. So here we go. Simulation. Here are the 4 steps of performing a simulation. Step 1, state. Ask a question of interest about some chance process. Step 2 is plan. Describe how to use a chance device to imitate one repetition of the process. Tell what you will record at the end of each repetition. Step 2 is one of the more important of the 4 steps. All right. What are you going to use to simulate this thing? How are you going to use it? And what are you going to record when you've done this? Okay, there's specific things you should have in your plan. Right? Are you going to use a dice, right? You're going to roll dice for the simulation. What are the numbers on the dice going to represent? Are you rolling 1 dice or 2 dice, right? How is this going to come together? What are you going to record after you roll the dice? Are you recording wins? Are you recording losses? Are you recording the sum between the dice? There's lots of different things that could occur, and you need to be specific about what you're doing. Right? That needs to be in your plan. Do perform many repetitions of the simulation. Right? Keyword in here, many, lots and lots. Conclude. Use the results of your simulation to answer the question of interest. All right, so here are our 4 steps. Right. In this do phase, perform many repetitions of the simulation. This is why I'm going to show you some ways that we can do a simulation and do it quickly at the end of the presentation today, because it can become very time consuming to do many repetitions of a simulation if you're not using some sort of software or application to do so for you, or you're not doing it in a group. Like for me to collect the data on what we did on Monday only took a few minutes because I had all of you guys submitting responses at the same time, and I was able to collect those and easily put them into like Staplet to create a graph and to analyze the data. Right, so using tools is going to be very important. Right. Does anyone need any more time to write down our 4 steps of performing a simulation? Okay. So next, right, we're going to look at the state plan do conclude using simulation that we've already seen, which is the 1 in 6 wins game. And for that, so for state, what's the probability that 3 or more of the 7 people who buy a soda win a prize if each bottle has a 1 in 6 chance of saying you're a winner? So this is slightly different than the question that we were answering on Monday, where I just asked, does it seem reasonable based on our outcome that they're saying 1 in 6 chance of winning? All right, this is a little more specific to the scenario that played out in the store where 3 people won out of the 7 that came into the store. Plan. Use a 6-sided die to determine the outcome for each person's bottle of soda. The 6 was a win. Right? We used that on Monday. 1 through 5 were considered no prize. Right? We did not essentially record that number. For the die, roll the die 7 times, once for each person, and record the number of people who win a prize. That's exactly what we did on Monday. Have each student perform several repetitions. Right? Again, that's what we did. And then the conclusion. Out of 125 total repetitions of the simulation, there were 15 times when 3 or more of the 7 people won a prize. So our estimate of the probability is 15 out of 125, or about a 12%. Seems plausible that the company is telling the truth. All right. So it's about 12% of the time, 3 or more people won with that group of 7 in the simulation. All right. So this is an example of setting up and going all the way through the process of running a simulation. All right. Are there any questions about the simulation or the steps in a simulation? Okay. Next. So we're going to look at an example from the textbook. This is a video. Hopefully you can make it work. Might go there. Go here. All right, and please let me know that you guys can hear this when it plays.
Hi, this is Jason Molesky. In this example, we'll take a look at how we can use technology to perform a simulation. Suppose in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. In each box of their cereal, they'll put one collectible card featuring a NASCAR driver, either Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. Now the company says each of the 5 cards is equally likely to appear in any box of cereal. Now suppose a NASCAR fan decides to keep buying boxes of the cereal until she has all 5 of the driver's cards. She's surprised when it takes her 23 boxes to get the full set. Our question is, should she be surprised?
All right, I want to point something out here. In the description of the scenario here, right, there's a key part. It says the company says that each of the 5 cards is equally likely to appear in any box of cereal. This is important in statistics. When something is equally likely, it means it's essentially fair. Each of the 5 cards has the same fair chance of being chosen or being in a box. This adjusts, or this could have an impact on how you do the simulation. Right? When things are equally likely, it's typically a little easier to set up. So just keep that in mind. We'll talk about what to do when it's not equally likely as well.
So for the problem, we want to answer the question, what's the probability that it'll take 23 or more boxes to get a full set of 5 NASCAR collectible cards? Since we don't want to buy box after box after box of this imaginary cereal, we'll let our calculator simulate the situation for us. So for our plan, we'll need 5 numbers to represent the 5 possible cards. Well, the easiest thing we can do is let 1 equal Jeff Gordon, 2 equal Dale Earnhardt Jr., 3 equal Tony Stewart, 4 equal Danica Patrick, and 5 equal Jimmy Johnson. Next, we can use the rand_int feature on our calculator to simulate buying 1 box of cereal and looking at which card is inside.
And real quickly, here is where you find the rand_int function on your graphing calculator. Go to the button that says Math. And then we need to use the PRB tab, probability. So click to the right 3 times to get to PRB. And we want that 5th option here, rand_int with a little open parentheses. So you can click down to it or just press the number 5. Now that's in our entry field here. All that you do is say the number range that you want a number from. Right, for this example, I think they're doing 1 through 5. So we would say 1, comma, 5, and close the parenthesis. And then you hit enter, and it gives you a number between 1 and 5. Right. Next one is 5. If you just keep hitting enter, it's just going to repeat the last command, which was rand_int 1 through 5. So you can just continually create random integers between 1 and 5. We're using integers, int, because integers are whole numbers. Right? We want whole numbers. We don't want to end up with decimals. That's a whole different ballgame. Okay. Any questions about the random integer function on your calculator? This is like the random number generator that's built into your calculator, essentially. Okay.
Whichever value comes up will correspond to one of the 5 drivers. Because we want a full set of cards, we'll just keep pressing enter until we get all 5 of the labels from 1 to 5. Then we'll record the number of boxes that we had to open. So, suppose we performed 1 repetition, and this is what happened. In our first pressing of randint15, we got a 3. In the next case, we got a 5, then 2, then 1. Already in the first 4 simulated boxes of serial, we've gotten 4 of the different drivers. But now suppose a 5 came up. We've now gotten a double of 2 of the cards. 2, 3, and 5 were already drawn, and finally we get a 4 on our 9th box. So in this repetition, it took 9 boxes to get a full set of 5 NASCAR driver cards. Then suppose in the next repetition, it took us 16 boxes, then 10 boxes, then 15 boxes, and finally a case where it took 22 boxes for us to receive the full set. Now, if we were to continue this simulation on and on and on for 50 repetitions, this is what might happen. This is a Fathom dot plot of a simulated 50 repetition case. Notice in this dot plot, there was never an instance where we had 23 or more boxes necessary to get the full set. In fact, in most cases, it only took around 10 to 12 boxes or so to get the full set. So for our conclusion, we never had to buy more than 22 boxes to get the full set in our simulation. So our estimate of the probability that it would take 23 or more boxes to get a full set is roughly 0. The NASCAR fan should be surprised about how many boxes she had to buy. For some additional practice with simulations with technology, try exercise 25.
All right, here we go. So, any questions about that example? And again, I'm going to put the link to this video. It's in the live class resources. So you can rewatch that if you like. It doesn't show the calculator part. I brought in the calculator. But that will be in today's video as well. So, let's get back to this. All right. So now, let's suppose we have an unfair coin, right? Not equally likely possibilities here. Suppose that the probability of flipping a coin was not fair, and that the probability of a heads was 0.6 and tails was 0.4. So there's a 60% chance of getting a heads, while there's only a 40% chance of getting tails. What would you have to do to simulate this properly? Okay, and so what we get here is, again, an unfair coin. So simply flipping a coin, right, like if you pull a coin out of your pocket and flipping it, which would be a fair coin, isn't going to work for this simulation anymore, right? So what we have to do is come up with another way of measuring success or failure within this simulation, right? So what I'm going to say is like, okay, well, this is, right, we have our 60% and our 40% essentially. So we're going to let heads be numbers 1 through 6, right, and tails be numbers 7 through 10. Right, so I'm going to use like a random number generator to simulate the coin flipping. So we'll use that random number generator from 1 to 10, which I forgot. Right? To simulate that coin. If we get a 1, 2, 3, 4, 5, or 6, that means it was a heads. If I get 7, 8, 9, 10, then I get tails. All right? So then the question is, what is the probability you will flip 3 or more tails in 10 flips of this unfair coin? All right. So we want to run a bunch of simulations on this. So using like the random integer function on our calculator could be very time consuming. Right? There's 10 flips for one simulation, one repetition of the simulation. Suppose I want to do this 100 times, right? 100 simulations. That's 1,000 times of hitting enter to get a random number and then having to keep track of it and right? That's a long process. So we want to use different tools to be able to simulate this. Okay. So what I've set up here, and first I'm going to say we want 3 or more. So that would be 3, 4, 5, 6, 7, 8, or even 9 or 10 tails, or 10 flips on our unfair coin, and we want the probability. So what are the chances? What's the percentage of 3 or more tails and 10 flips of a coin? Right? So let's look at what we've got set up here. So I'm going to leave this part. Yep. And go to, okay. We'll reset this one up. All right, so here I've got Staplet open, and I'm just on the one categorical variable single group section. Right here, let's show where that is. All right, one categorical single group. It's just this one right here, because I'm measuring. In this example, I'm doing heads or tails. That's not a quantitative variable. That's categorical. All right. Whoops. Still today. There we go. All right. So we have coin flip outcome. We're going to do counts, right? Because what I can do is I can set up like the proportion that I want, right? So I'm going to have heads, and I'm going to say that happens with a frequency of 6, and we'll have tails. That happens with a frequency of 4. And I'm doing this because I'm representing 10 coin flips, and with the suggested unfairness of the coin, we have a 60% chance of heads, or 6 out of 10, and 40% chance of tails, or 4 out of 10. So that's how I've set this up. We'll do our analysis. We'll just say relative frequency so it shows percentage. The bar graph is what we would expect it to be. It's 60% heads, 40% tails. This is the hypothetical probability based on the problem scenario. So now what we can do is down here we have perform inference. We can run a simulation right here. We're going to simulate sample count of tails because that's what I've been asked about. Simulate the distribution of the sample count for samples of the original size, assuming that the true percent is equal to the observed value, right? Because we've set it up to be out of 10. And it's the correct proportion, 60% to 40%. Right? And it is inference procedure, simulate sample count. The sample count was 10, so it's going to do out of every 10, how many things did we have? All right, and I'm going to add 100 samples. And we'll say add samples. And almost instantaneously, we get a dot plot showing the number of tails that occurred in each set of 10 flips of the coin. All right, so we did 100 samples right? Our mean was 3.71, standard deviation is 1.659, right? So each of these represents, okay, well, there was 1, 2, 3, there's 5 times where only one tail was observed, right? There was 4 times where 8 tails were observed in 10 flips of a coin, right? 2, 3, and 4 seem to be the most common. But here's what else we can do. I can say, okay, count the number and percent of dots greater than or equal to 3. That's what I've been asked about. What's the probability of getting 3 or more, right? And then so we're at 3 or more, and we're going to count. So it shows me 3 or more, right? There are 73% in the selected region. So this is saying there's a 73% chance of getting 3 or more tails, right? Given the unfair coin. All right. And that's based on the 60-40 unfairness. Now, there's a pretty high percentage, but that also makes sense because the probability says out of 10 flips, I should get about 4, right? That's what it should over time be. Every 10, I should get 4. So this is saying the chances of getting 3 or more are pretty high because that's better than the probability, right? If I were to change this to 4, right? The probability changes, right? It has a 51% chance of being greater than or equal to 4. As I go up, well, let's say, what is the probability of getting 5 or more, which would be closer to that 50-50 traditional fair coin, right? Our odds go much farther down. Okay. But again, we're only looking at 3, and we can easily add more samples and see what changes. You can add 100 more just by saying add samples, and it's still pretty high, 78.5. Add more samples, 79.7. Right? As we add more and more and more, this percentage should change less and less and less, and gets to where we'd expect it to be, or what we would expect. So in answering the question, we can say, well, based on our sample, our simulation here, it's about 80% chance that you'll get 3 or more tails. Right? So Staplet has it set up where you can kind of easily create a simulation scenario, so that's kind of nice. I've also set it up on Excel to where I've created a 100 simulations. Right, so this is using the same random number idea. Numbers 1 through 6 represent heads. Right? 7, 8, 9, and 10 are tails. So over here, we have the outcome of each flip along like the top here. This was simulation 1. There were 3 occurrences of tails. Right? We had 9, 9, and 8. And this row is counting how many times I have a number that is, well, it's less than or equal to 10 or greater than or equal to 7. That's the way that it gets set up. This is a little more complicated, but the nice thing with Excel is that you can easily kind of manipulate and change what you're looking at if you need to. In this case, I had it count how many times I had 3 or more. Then I did the percentage, this number divided by 100, 85%. So this simulation came out pretty close to the other simulation. So there's that. So there's a few different ways you can do it. Excel's a little bit harder to get set up as opposed to Staplet, but there's options. All right. And that's it.